A study on performance of standard-grade bacterial concrete with fly ash. Abstract concrete is prone to micro-crack formation, which is undesirable because they provide an open pathway for the ingress of water and other deleterious substances. Main reason to prevent cracks or limit crack width is to enhance the durability of the structure. Concrete surface treatments with waterproofing materials to prevent the access of aggressive substances are a common way to repair concrete structures. These cracks should be repaired to increase the strength and durability of the structure, using either epoxy injections or latex treatment. However, the most common surface treatments include using organic polymers, epoxy, acrylics, and polyurethanes. The characteristics of pore structure of concrete have a direct influence on its durability. One way to avoid costly manual maintenance and repair is to incorporate an autonomous self-healing mechanism in concrete. One such alternative repair mechanism, i.e. a novel technique based on the application of biomineralization of bacteria in concrete. The bacteria present in the concrete rapidly fill cracks through calcite production. The search for new environmental-friendly construction materials like fly ash, which can improve the strength and durability of concrete structures, has developed interest in self-healing bacterial concrete with fly ash. The present experimental investigation is carried out to study the mechanical and durability properties of M40 grade concrete using Sporosarcina Pasteurii, which would make it self-healing. The bacterial concentrations were varied by 105, 106 and 107 cells/ml. The percentage replacement of fly ash used were 0%, 10%, 20%, and 30% by mass of cement. The experiments were carried out to evaluate the effect of Sporosarcina Pasteurii on the compressive strength, split tensile strength, flexural strength, strength loss, and weight loss at 7, 28, 56 and 90 days. The test results indicated that inclusion of Sporosarcina Pasteurii with mix 1x106 cells/ml bacteria and 20% fly ash gives optimum performance in terms of compressive strength, split tensile, and the mix with 1x107 cells/ml bacteria and 30% fly ash gives optimum performance in terms of strength loss and weight loss and acid durability factor. Keywords: concrete, self-healing concrete, fly ash, bacteria, mechanical properties, durability. 1.0 Introduction. Rapid growth and development in the infrastructure can be seen over the past 100 years in the construction activities. In this development, concrete plays an important role in the development of the infrastructure in the day-to-day life. Among all the building materials, concrete is the artificially made building material which has got special characteristics. The major drawback of concrete is its low tensile strength, due to which microcracks occurs when the structure is subjected to sustained loading and exposed to aggressive environmental conditions, results into decreasing the life of the structure. Entry of harmful chemicals through these cracks may result in concrete deterioration through chemical attack and can also cause corrosion of steel reinforcement. This corrosion leads to increase in crack damage, resulting in loss of strength and stiffness of concrete structures. Even though there are many crack repairing techniques to reduce the extent of cracking by available modern technology, there are a large number of techniques to repair cracks in concrete, such as grouting, gunneting, sealing with epoxies, and many more. However, the above-mentioned techniques are costly and also in high maintenance cost. In order to overcome this, a special type of concrete is developed with the introduction of bacteria in concrete, which results in bacterial concrete. This is also called as self-healing concrete. In view of the global sustainable development, it is imperative that supplementary cementing materials be used to replace large proportions of cement in the concrete industry. The most available supplementary cementing material worldwide is fly ash, a byproduct of thermal power stations, which indicates that there is a potential for the use of much larger amounts of fly ash in concrete, and therefore, for significant reductions in cement production, resulting in considerable environmental benefits. To considerably increase the utilization of fly ash that otherwise is being wasted, and to have a significant impact on the production of cement, it is necessary to advocate a use of concrete that will incorporate large amounts of fly ash as a replacement for cement. An attempt is made to study the properties of bacterial concrete using Sporosarcina Pasteurii, Bacillus pasteurii, along with fly ash as partial replacement to cement. Bacteria. The bacterial concrete is a concrete which can be made by embedding bacteria in the concrete that are able to constantly precipitate calcite. This phenomenon is called microbiologically induced calcite precipitation. It has been shown that under favorable conditions, for instance Sporosarcina Pasteurii, Bacillus pasteurii, a common soil bacterium, can continuously precipitate a new highly impermeable calcite layer over the surface of an already existing concrete layer. Microbiologically induced calcium carbonate precipitation, MIC, is comprised of a series of biochemical reactions. In this process, An alkalophilic soil microorganism, Bacillus pasteurii, plays a key role by producing urease that hydrolyzes urea to ammonia and carbon dioxide. In aqueous environments, the overall chemical equilibrium reaction of calcite precipitation can be described as: bacterial spores are specialized cells which can endure extreme mechanical and chemical stresses, and spores of this specific genus are known to remain viable for up to 200 years. Spores are dormant but viable. Bacterial spores immobilized in the concrete matrix will become metabolically active when revived by water entering freshly into the concrete. 2.0 Research significance. Cracks in a concrete structure reduces the life, and cracks of dimension smaller than that of cement, micro cracks, cannot be filled with chemicals. Crack treatment processes involve harsh materials such as cement and chemicals, adding to the pollution of environment. There have been instances of allergic reactions due to chemicals faced by the inhabitants and handlers. Bacteria secretes calcite which fills the cracks, and compressive strength and durability of concrete is improved. The environmental impacts of poor disposal of mineral wastes like fly ash, GGBS, need to be addressed. Use of fly ash in the manufacture of concrete reduces its interaction with the environment, as well plays an important role in imparting strength and durability to the concrete. As there is limited literature available on the study of properties and characteristics of such combination, it is intended to investigate in this direction. 3.0 Materials. 3.1 Cement. Ordinary Portland cement of 53 grade available in local market conforming to specifications of IS 12269 to 1987, having specific gravity of 3.06 is used. 3.2 Fine aggregate. Locally available clean, well graded, natural river sand conforming to specifications of IS 383-1970 having specific gravity of 2.50 is used. 3.3 Coarse aggregate. Crushed granite angular aggregate of size 20 mm nominal size from local source with specific gravity of 2.65 is used. 3.4 Water. Locally available potable water conforming to IS 456 is used. 3.5 Fly ash. Fly ash of class F with 2.32 specific gravity is used. 3.6 Microorganisms. Sporosarcina Pasteurii, a soil bacterium which is cultured and grown at Laboratory of Biotechnology Department, CBIT, is used in 105,106 and 107 cells/ml concentrations. Calcium lactate is added by 1% of mass of cement. 3.7 Grade designation, M40 grade concrete. 3.8 Culture of bacteria. The pure culture was isolated from the soil sample and is maintained constantly on nutrient agar slants. It forms irregular dry white colonies on nutrient agar. Whenever required, a single colony of the culture is inoculated into glass bottles containing nutrient broth of 13 grams in 1000 ml of distilled water, and the growth condition is maintained at 37 degrees Celsius temperature. The medium composition required for growth of culture is peptone, 5 gm/lit, NaCl, 5 gm/lit, yeast extract, 3 gm/lit. 3.9 Maintenance of stock cultures. Stock cultures of Sporosarcina Pasteurii were maintained on nutrient agar slants. The culture was streaked on agar slants with an inoculating loop, and the slants were incubated at 37 degrees Celsius. After 2 to 3 days of growth, slant cultures were preserved under refrigeration, 4 degrees Celsius, until further use. Contamination from other bacteria was checked periodically by streaking on nutrient agar plates. 4.1 Compressive strength test. In the present investigation, compressive strength is determined as per the procedure given in IS 516:1959. Compressive strength is determined on 150 x 150 mm3 using UTM at a loading rate of 140 kg per centimeter 2/min. Compressive strength equals P/A. P. Maximum load applied on the specimen during the test in Newton. A. Cross-sectional area calculated from the mean dimensions of the section in mm2. 4.2 Split tensile strength test. A diametric compressive load will be applied along the length of the sample at a continuous rate until failure occurs. This loading induces tensile stresses on the plane containing the applied load, causing tensile failure of the sample. IS 5816:1999 formed the basis for the development of this procedure. The measured splitting tensile strength of the specimen shall be calculated using the following formula: FCT equals 2P/dl. P equals maximum load applied on the specimen during the test in Newton. L equals length of the specimen in mm. D equals cross-sectional dimension of the specimen in mm. 4.3 Durability, acid test. The chemical resistance of the concretes was studied through chemical attack by immersing concrete blocks in an acid solution. After 28 days period of curing, the specimens were removed from the curing tank and their surfaces were cleaned with a soft nylon brush to remove weak reaction products and loose materials from the specimen. The initial weights were measured and the specimens were identified with number. The specimens were immersed in 5% H2SO4 and HCl and reading for weight and compressive strengths were recorded for all mixed types at 7, 28, 56, and 90 days. The solution was replaced at regular intervals to maintain constant concentration throughout the test period. Acid durability factor, ADF, can be designed as follows. 5. Acid durability factor, ADF, equals sister n/m. Where senior equals relative strength at n days, %. N equals number of days at which the durability factor is needed. M equals number of days at which the exposure is to be terminated. Acid attack test was terminated at 90 days. So, M is 90 in this case. 5.0 Test results. 6.0 Microstructure. Scanning electron microscope, SEM. The microstructure of the fly ash-based bacterial concrete with different calcium contents was observed by SEM. It was notable that the figure 7 of normal concrete matrix was not homogeneous and contained small pores and cracks. Figure 8 indicates normal concrete sample which had no depositions of calcium carbonate, whereas figure 9 shows good amount of calcium carbonate deposition on the surface and less number of pores are seen in comparison to the samples of normal concrete. Figure 10 shows a reasonable amount of calcium carbonate content along with fairly good amount of silica, and this is due to addition of fly ash in the concrete. And it is consistent with the values of higher compressive strength for bacterial concrete and bacterial concrete with fly ash compared to normal concrete. From the micrographs of figure 9 and figure 10, it can be seen that increase in calcite content in white color formed on the surface and fly ash particles resulted in a more compact and denser matrix filling the voids and cracks in the concrete, improving the pore structure of the concrete. Due to reaction of silica with free lime at later age forms calcium silicate hydrate compound. Because of this hydrated compound, the values of compressive strength for bacterial concrete with addition of fly ash are higher at 90 days compared to normal concrete. 7.0 Discussions. In M40 grade concrete, the compressive strength is increased by maximum of 17.8% at 90 day for 106 BCF20 when compared to conventional concrete, as fly ash has the property of gaining strength over longer period, and it is observed that compressive strength is decreasing with increase in fly ash content. The maximum splitting tensile strengths obtained as 4.6 MPa at the age 90 days for 106 BCF20. Increase in compressive strength and split tensile strength values is due to the reason that the density of the concrete has been increased due to filling of cracks with calcium carbonate crystals secreted by the bacteria induced in concrete and fly ash gaining strength at later age. It is observed that weight loss percentage for 107 BCF30 is 5.61% compared to normal concrete of 6.91% at 90 days of immersion in H2SO4. It is observed that strength loss percentage for 107 BCF30 is 10.21% compared to normal concrete of 13.66% at 90 days of immersion in H2SO4. Acid durability factor is found to be high for bacterial concrete 107 BCF20 as 90.68 compared to 86.34 of normal concrete. 8.0 Conclusions. Concrete mix 106 BCF20 with 1x106 cells/ml bacteria and 20% fly ash has given maximum compressive strength and split tensile strength compared to other mixes. Concrete mix 107 BCF30 with 1x107 cells/ml bacteria and 30% fly ash has shown better performance in durability properties like resistance to acid attack compared to other mixes.